So today I thought I'd show the machine I've retrofitted. So you've probably seen this control circulating Alibaba, and I've probably retrofitted maybe 7 machines with this control so far, and I've retrofitted 2 machines with their whole package. So you can just get the control and the output boards, or you can get the whole servo drives and servos. And this one I've gone with everything, and this one I've gone full 5-axis, even though you can see it's just 3 at the moment. But someone wanted this machine, they paid me to do it, so it's going to be out the door fairly soon. The only stipulation is they wanted a tool changer on it. So like most machines in this kind of format look like this. They have a manual drawbar through the front. This particular machine has a powered drawbar, and these are kind of like an air ratchet. They're really violent. They're great at cross-threading screws. So basically this is the tool that goes in that machine, and then this drawbar through the middle pulls everything tight. And this was the drawbar for this machine, but we've done something a little bit different. So a proper CNC has like a pull stud which pulls the tool into it, and then it has a stack of Belleville washers to kind of put pressure on this, and they're normally hidden inside the spindle, but because this was never designed to do that, I've had to put them on the top. And these washers are much bigger. Normally they're only like maybe 1 3/8 inches, and they stack maybe 16-inch long. But because I can go with bigger washers, this stack compressed is I think 4.75, and then uncompressed is about 6-inch. And that's 1,600 pounds of force on that. But to release the tool takes about 2,000. So this pneumatic cylinder is a 5-inch bore, and I need between 110 and 130 psi to actuate that. 6-inch would have been better, but I had to make do with what I got. And it's currently just hooked up to a compressor, but if I press this, it's going to actuate the cylinder like that. Releases the tool, so you can see the pull stud. See, that's all compressed up there, and then I can put it back in, release, and it's just like a regular CNC. I'm not sure anyone's ever done this on one of these machines before. The other thing is, this collar was made along with some modifications inside the spindle, which I'll show later, that kind of secures the quill in place. It means the quill could never move again. So I removed all the mechanism just so no one, puts in the wrong gear. The gear change, the high and low still all works, which is good. So I'll switch this on. So I did all the electrics myself. I've got quite a bit of a background in it. To save cost, the isolation is just through a switch and a contactor, because this machine is on a plug, a 220-volt plug. If it was wired straight to 3-phase, then yeah, it'd have to have a proper disconnect. But because it's on a plug, I can kind of cheat and just put a contactor in there. So switch it on. All that switch does is close the contactor and then supplies power to the rest. It's all fused, obviously. So when I press the on switch, the contactor will close power to the control transformer, and then it'll supply power to everything else. Basically, the spindle drive and the servo drives all have a contactor between them and fuse. So when I press the on button, that supplies power to all these contactors. So this machine was always a CNC. These do exist. They came from factory like this with ball screws. So I'll just let it boot up. But I'll show inside the panel that basically this is now shut, so the spindle drives on. These 3 relays are closed for these servo drives, And this is a 5-axis control, so all these, which I put a pinout diagram, allows for an extra 2 more servo drives. This is also closed loop feedback, so the encoder from the servo goes to the drive, but there's also feedback coming from the drive back into the control. And then there's, you know, maybe 20 inputs and outputs that you can do what you want with. So I'll just show quickly the prototype I made. So this is the prototype. So we had to machine this pocket in there for the tool grabber. So when it pulls in up to here, pulls the tool in, then closes down. And then when it pushes back out, it can spring open and release the tool, which is pretty cool. Now this machine is the first time I've gone with absolute drives, absolute encoders. So you boot it up and it's just ready to go. There's no need to home it or anything, it knows where it is. It's currently in metric. All my other machines are in imperial because this is Canada and everything's in inches. In the industry anyway. Same with America, same with the UK. Nice and quiet. Set a spindle going. You can see everything's nice and pretty. I was worried that I might have to put an extra set of bearings on there in case it wobbled, but it doesn't. So that's full speed, no vibrations, it's all good. Obviously you don't want to release the tool while it's like that, and you also want to make sure there's always a tool in, because then it would rub on the actuator. So this control does basically everything the CNC would. Now it's got the tool changer. You could, you know, put some stations on there, do tool changes. But this person, they're just going to release it by hand, which is probably faster actually if you stood at the machine. Not much else to say. This control is just like any other CNC control. Does everything great. The only thing, if you want to do rigid tap-in, is obviously you need a spindle encoder, which is simple enough. But everything runs on pulse and direction on these newer machines. You go to an older CNC and it will run on a analog signal, so plus 10 or minus 10 volt, and that directs the direction of the motor and the speed. So 10 volt would be full speed, full torque, everything. And then an encoder off the servos goes back to the control, and it's a big closed loop system. And all the controls, you know, they needed some tuning, but they were built from the factory. But to retrofit those, it was quite a pain in the butt. So most people just replaced everything. But this control goes with step and direction, along with on the spindle positioning. You have to get their own spindle drive, which does step and direction for the rigid tapping. Otherwise you can just do with a floating tap, and it still uses a spindle encoder, but you want to use a floating holder. You don't want to just put it straight in a collet. I wouldn't trust it. But everything else is great. I've run one of these for 3 years now. Put in, like, you know, between 5 and 10 hours a day on it. So it's a SZGH. They do different models. This is set up for 5-axis. As you can see, all my other machines are 4-axis. And one in the very back, the 4th axis is used for the tool changer. So really I need that to be 5-axis if I want to put a 4th axis interpolator on there. You know, manual mode, hand wheel mode. Super quiet, they're really accurate. These are 1 kilowatt, and there's crazy amount of torque in them. Enough torque that you'll just push this head out of skew before you alarm out the servo. And I'd probably say that's it. And as for speed, I put this at 4 meters a minute, which is about 200 inch per minute. This will go way up to like 1500 inch per minute, real fast, like 20 to 30 meters a minute. But you shouldn't really do that on a boxway. It's not great for them. You should just save that for linear rails. But yeah, it's quite a neat machine. It's all on boxes, so it's pretty sturdy. The only thing I don't like about it is this drive's probably like 15, 20 years old, and it's all running on single phase. So I did this because it can go in someone's home garage. And single phase just puts more strain on these. Say I'm using 5 horsepower spindle, this would need to be 10 horsepower of drive. So like this one's on single phase. This one's a bit more scabby, but it's got a nice new control. That click you heard was the automatic lubricator. So every between 10 and 30 minutes, it will dose some oil and shove that, you know, to all the ball screws, all the ways, everything. And then there's also some end pieces on here which help cover the ways. Like the ways on this machine are really good condition, as you can see, like really good condition, which is a bonus on these. Like the other ones, they're all chewed up at the ends, so it still works, but like this machine I could mill anywhere on the table. That machine, if I want to do really accurate or rigid work, I would just want to stick to the middle of the table. And that's it. Thanks for watching. This machine is going to be gone soon. I'm getting like 10 pallets of material in here in the next few days. And then I got some really cool projects down there. I'm trying to sell off the machines I don't use, like this one, that one there, keeping obviously the wire EDM, that's really cool. And then there's another Cincinnati lathe down there, which I think I'm going to get rid of. And then I'm going to do a couple of cool projects, like I got the V12 down there. I designed a 12-speed sequential for that with a twin disc clutch. But I'm going a different direction and making a motorcycle with it, with a 2-speed sequential. So that's going to be really cool. And then I'm going to use the wire EDM to cut the gears for that. And then hopefully I'm going to cast the casings out of aluminium, do some heat treating, and then mill it out, and then yeah, do it properly. So thanks for watching, and I can switch this off. Don't need to hit the E-stop. That's the older machines used to need that, because the E-stop, there's a circuit for the brakes on the motors. So if I pressed off, sometimes the spindles will drop on different machines, including lathes. But this doesn't have brakes, it's got a counterweight, doesn't matter. But that's the reason you hit an E-stop on other machines, is it switches off the brakes, sorry, switches on the brakes, I guess. Disconnects power anyway, and the brake goes on. And it switches off all the servo drives and everything before you switch the machine off. Doesn't matter on this. And it's absolute, so it's always going to know where it is. And the quality of this thing's great. I think the control, the 2 panels, all the electrics, the drives and the servos came to about, I'm going to say about $2,400 US delivered. But yeah, I thought I should show this because this is just obviously really cool. There is a bearing in there as well, because you don't want to put the force on these castings, they'll just snap apart. So this is kind of isolated almost to this, even though there's a big drawbar pulling everything, pulls this. The only force you get is when you push this down to release the tool, you will get a bit of force on the castings, That's just to knock the tool out of its spot. And the homing switches, I don't need those. I put them all in there, but obviously it's absolute, it doesn't matter. The only time is if the batteries go dead, you might use the homing switches to find the endpoints, and then you can tell the drives, this is the end, don't go past that, which is really simple. Yep, thanks for watching. So here is the design for the tool changer. Let's do a cross section. So you can see this is the tool with the pull stud, and then the puller pedal. So when the pedal hits this, it closes down, pulls the tool in, and then when this moves back out, it pushes the tool out. These open out into the groove and the tool releases. And then there's a drawbar through the middle of the tool, which is compressed by these Belleville springs. Then this bearing kind of supports the whole thing, but the force is basically between the outer spindle and the drawbar. And then this piece here kind of guides the Belleville washers to stop them moving. And then the cylinder. So this will push it down. Either the springs bottom out or this bottoms out. And that's it. Pretty neat.